Hello. I would like to invite you to the roundtable organized by the World Group 4 of the Hydropower, which is titled Future Horizons of Hydropower and Integration with Other Renewable Sources. So it corresponds to the third goal of the third year of our working group. And we'll talk about challenges, we'll talk about problems, and also talk about opportunities integrating not only conventional hydropower with other renewables, but also we'll talk about energy sources that we talk about perhaps really on this hydropower cost action, for example, marine energy or geothermal energy. So without further ado, I want to present you our first speaker, which is Milena Raic. She's an assistant professor at the Faculty of Mechanical Engineering, University of Niš in Serbia. She holds 2 PhDs, one in mechanical engineering and one in technical science. Her professional focus lies at the intersection of renewable energy, sustainability, and engineering innovation. She has strong commitment to applying technical knowledge for practical improvements in energy and water system. And she's recognized notably through National Award for the Best Doctoral Dissertation contributing to Serbia's economic environment. She is also a task group leader of the Work Group 4 on renewable energy and hydropower coupling. So, Elena, the floor is yours.
Thank you so much. Can I ask you for the maybe point?
Yes. Yeah, thank
you. Thank you once again. My name is Milena Raic. I'm coming from University of Niš from Serbia. Originally, I'm a chemical engineer in hydropower sector, but I did my PhD in field of stress strain analysis, not only in hydropower, but in general in pressure vessels and similar also units. The other PhD was also concerning my staying in my Department of Industrial Management. So I'm really actively involved with the cooperation with industry, especially with the innovation projects. Today, I will tackle the subject, also present you some findings concerning the LCA method that should be and can be also applied in this of projects, but concerning the future solution in hydropower, concerning the integration with the solar or maybe wind with all the hydropower, we also concerning this analysis. So where should I? Should maybe do the
Right, the first line. Right now.
So I can maybe switch to be there and then to change.
We will change the presenter.
Okay, thank you. In the beginning, I want to mention that LCA method was also, part of the most ongoing and also future projects. The thing that we have not also reconsidered in many projects now is a basic. One of the basic, sections that need to be done. And I want to say that it can address some things that we should also think that we should also take in mind, but also to present our solution in a better way. Having all the presentation that we have also heard this morning and yesterday, we'll still concerning about the social acceptance of these units, hydropower plants, and that I think with detailed LCA methods conducted and also results, we can achieve this social acceptance in a better way. It is the basic challenge that we should also consider is the data, the actual data that should be implemented, but I will also include this in this discussion. Also wanted to mention that all the LCA methods, also approaches were considered under the standard ISO 14040 and 4044. And concerning the ongoing challenges that is like concerning this type of analysis is also the how to say variability in the outputs of the results. We can find different studies. For example, when we are talking about the results of the intergovernmental panel and climate change, like the asymptotes or the some also results that they have they like as a final output for the hydropower, we have the 24 grams CO2 per kilowatt hour concerning only the operational phase. And also for the Europe, we can also we have the really huge, how to say, range from 1 gram to 2,200 grams. It depends also of the location, but also the type of a plant that we want to consider in our analysis. So it should be really, how to say, sensitive to this approach and then to use the actual data for our analysis. I also find the data that, for example, the run-of-the-river hydropower, it can be in the range from 1 to 24 gram CO2 per kilowatt hour, and for the like the tropical reservoirs, because of the methane, we have a bit higher. From 150 to 220 grams CO2 per kilowatt hour. One how to say the concerning impact of the LCA method here in the hydropower is of course the land use. During the construction phase, the huge area of the land is being used for the build, but we will see now what the actual results show. Is it like something that should be considered in our like final analysis, or we should only focus on the operational phase? But as the end, like what should we consider like the most like a challenge is to need some standardized and detailed data for each is like use case that we are like analyzing and using. And also from some also regional data, it is really important to note because Southeast Europe is completely different with, like, for example, the like the also Norway that also can be also taken into account. And there's also in the literature still some inconsistencies in the applied methods. So we should be really how to say sensitive to this, which method should be applied and how. Here I also covered the overview of the digital tools that can be used, because I think it is really important for the industrial perspective and also from the academia. What can be used in what manner in order to have the proper result that can be also used as an input to an analysis. I want to mention concerning the hybridization that we want to talk about today, about the future plans of the hydropower, in order to integrate the hydropower with the PV or maybe wind turbines. How effective concerning the LCA methods are they exactly? And I want also to put some researches that are not mentioned, so obviously because I'm not populistic, but I only want to have this in mind, because we are always talking about the negative sides of the hydropower, but concerning the negative sides of the other power plants that we have also. Concerning the PV panels, it is considered that we really need a huge amount of rare elements that we like are not like the renewable sources that we use. For example, 20 to 80 grams CO2. Even though they have this emission, they need 3.5 kilograms of silver and also 30 kilograms of copper per like megawatts of solar energy. And also we have some data concerning the fire, like these wildfires that happen in a solar power plants. It is the data from 2020. Yes, we have more than 130 solar fires only in 2020. Yes, happened in 1 year. So we should also consider this negative impacts. And also we heard yesterday that these, how to say, extreme events and accidents actually learns us something to reconsider our decision and maybe to find some other solution. Also concerning the wind turbines, I need to also mention about this disposal, how to say, phase, because if you want to look to the LCA, we are concerning the boundaries from this cradle to grave. Like we need to also see this final phase, how it can be solved. It can be solved, and it's like the negative impact of this energy that we want to present as a renewable new and like as a useful. And then in having this in mind, we can also concerning what are like the basic steps of the LCA method that should be applied. We need to define for any analysis like the boundary conditions and also to see the goal and the scope or what you want to achieve. In the projects, mainly these are like the already tasks that are like presented to us, and also should we like compare this solution to another one to find some another how to say scenario or not, and maybe to see only in the operational phase how we can impact the green gas emissions like positively. Then we are like doing the second phase, which is the life cycle inventory. It includes all the inputs concerning all the materials used, the fuels, water, but also the outputs, emission, waste across the whole life cycle. So it is always a question: should we here analyze this construction phase because you're like having the turbines product in some country and then distributed to the actual plant, or we should also exclude that and only point out to the operational phase, which I think is the important part. For this phase, we also need to take into account the concrete and steel, like for this the dam construction, but also the turbine and generator, also manufacturing, land use changes as well, and also the impact that this reservoir like will have to the environment as well. And then we are going to the assessment itself. It has like different impact categories. Where should we like analyze? You have the final output, like the global warming potential, for example, water use, but also biodiversity loss that we also consider in many analyses that we have. But also the acidification and also eutrophication and land occupation, and also how we change the internal landscape. And then the end interpretation is really important because the results that we have, we can interpret them positively or negatively. So it is really important to see what are like the hotspot that we should pay certain attention. And this is like the example from the actual use case from the system boundary of one hydropower plant. The analysis was done concerning the actual and the possibility to do the hybridization. I will also present here. This is the database that used the P also equivalent of the Gabi software application. When we define all the boundary conditions, we can also input all the data concerning all the inputs and outputs, and then see what we have of the like final data and how we can interpret that. And also, I wanted to present a comparison for the hydropower and also renewable that we did for some, how to say, use case scenario for one project proposal that we wanted to submit. It is like was not obligatory; it was an optional part to provide some calculations. So even though we know that in the hydropower we use huge water use, of course, in the commissioning phase, but concerning the green gas emission, we can see that the hydropower is not so bad solution concerning the same capacity that we have with the solar PV. But I will talk about it more detail later. Then, in order to, how to say, provide the suitable database for this analysis, European Commission made some, how to say, approaches or the weight, how to say, factors in order to propose the solution, how we should conduct this analysis. Everything is done on the, how to say, recommendations and some guidelines. We don't have a completely strict, how to say, a standardized process to be done. But here we can see that these weight factors were excluded from the guideline from the 2021, developed by the JRC and recommended by European Commission concerning the climate change, but also acidification, fresh water, ecotoxicity, water resource depletion as well, but also the environmental footprint. So we can see this is the for the hydropower, solar, but also wind. We have onshore. What is the weighting factor? Also, hydropower, like this weighting factor, how it looks like, and also solar PV and wind onshore weighted. So I think I answered here. Yes, the final result. We can see the score that wind onshore will have, like according to this guideline, 10.3. Hydropower score is 22 and solar PV score is even higher, 31. So we can see that hydropower in this can be also, how to say, recommended solution, especially with we have like the mini hydropower plants in some areas to be included, concerning like, for example, the solar power plants. Then I wanted to also present today the solution that can be really useful, not only for the academia, but for also for the industry, in order to implement this analysis, how to say, deeply, and concerning all the guidelines, we need appropriate software, appropriate, like to say, these digital tools. It's not, how to say, it's important, which like the basis we are like considering, and which we all want to include. So I took here, I think, 4 or 5 examples. What is like commonly done, this analysis in which software. For example, OpenLCA is most commonly used in academia. So having that in mind, that is open source, and also all the data that we can use. For example, EcoInvent is also open source, and we can use it here. For the technical expertise, it is like you have all the beneficials and can be really easily used and implemented in the modeling. Also can be really used to educate the students. So it is really, how to say, commonly used software, but has some other challenges. But concerning like the industrial application, there is like a SIMA Pro that is more advanced, have the more detailed databases, and also it is really suitable for some detailed industrial comparison and also analysis. The impact assess methods are also done as in Opel AC, this recipe, CML, and also a track. And also it also uses EcoInvent, having it in mind this EcoInvent, the, how to say, things that are concerning the hydropower and also integrated hydropower with other solution. It is really easy to also use it. Then we have a Gabi software that is also used well in academia, but also in industrial environment. Also, it is paid software. Heavily good integration with other databases, so you can easily use the outputs from the other analysis concerning the how to say, engineering approach. For me, Gabi is the most like suitable one, because you can see the process as a whole, so you can always determine the specific boundary conditions that you wanted to apply for specific case. It also what is the like the benefits? It also include the databases for the regional cases, so it is really like the added value concerning the others. We have also Umberto, and it is really used in industry as well. There is some cases, but the limited one, specifically that I only review reports and also the articles, so I find only like few one done in Umberto. And the one that is really, how to say, is in growth is the right one tool. But it is, how to say, really advanced software. You need to have the pre-knowledge in code, encoding, having that in mind that the Python is the, how to say, the main source of giving the input data and also outsourcing it. But the numerous studies done in this year, specifically the end of the 2024 was done in Brightway, specifically for the hydropower sector. So I'm assuming that for the future analysis will be more based to this solution. And then I didn't include here. I also wanted to present the comparative, how to say, approach for this analysis. But I can be also added to my like presentation and submit it to you like later if you want to include maybe the LCA method in your like curriculum for the academia like development or maybe in the future projects. And in the end, I want to assume some consideration concerning like the challenges that we were having like now in the project. The data and like the limited ability of the data is the major concern. Having that in mind, the LCA was not previously done in already, how to say, built hydropower plants, but having all the new projects that will be developed, designed, and also executed, I think it will be like necessary to include the LCA method specifically into it. And then concerning the industrial application that we should also consider, we should also maybe take a note that all these databases will be, I think, available more like in little way this year or another one because the LCA is growing really fast, like specifically the case that is done in this area. But concerning the hybridization of the hydropower plant with the other, like the energy sources, the studies that I review provide really better results than if you want to analyze solely the hydropower plant also or solar PV panels, but it also depends of data use and some specific project cases because it is not how to say, still a standardized method to this approach. Thank you for your attention. If you have any questions.
Yes, thank you, Milena, very much for your presentation. I think we can take a couple of short questions if anybody has a question. Yeah.
Thank you very much for this nice overview. I just have a question. Yeah, so the main source for greenhouse gas emissions comes from the methane that is gassing out of the CO2. And obviously, there's a big difference where you're located with the location you are. Coming from Iceland and having grown up in the Alps, in high alpine areas and also in the Arctic, organic material is very the organic material coming into the reservoir is very small. So I was just wondering, in your analysis, did you come across any specific regarding to the methane outgassing because of less organic material coming in? And also one thing I was wondering, in Iceland, we are now looking into the CO2 absorbs to particles. They settle out into the reservoir, and this could potentially give a negative carbon footprint because if you have CO2 that absorbs to particles and settles into the sediment, you would have a carbon sink having actually a negative carbon footprint. So just wondering.
Yes, I can hear you. Thank you. Yes, concerning this data, it was the case studies mostly done in the south, Portugal, but also what I also include here. So Iceland was not like the case study that I analyzed here. I read about that specifically when we started our task, like the last year. So I think if we like want to do all the inputs also in the LCA analysis, it can be also done. Me specifically haven't done that. So like in like detail way, I only did like the case studies for some of the project proposal, how to say for the mini power plants, in order for like our region, for the Western Balkan region. But it is very interesting to see if there is already done and how will like this method will have this approach to this like negative greenhouse solutions. Thank you.
Okay, thank you. Yeah, maybe one more.
Yeah, thank you. I have really I never understood all these things because when making a new reservoir, I read, that there are so many trees which will be flown and submerged, and this produces a lot of CO2. But isn't it that something most simple to understand that these trees should be first cut and used as a wood? I I don't know, maybe I understand all these things wrong, or there are so different views on that, what should be done and what not. This is really so contradicting in my opinion. What's your
Okay, that I agree with you. Since I read like numerous like studies having the positive and negative, like how to say, approach to the analysis itself. As an engineer, for me, it will be really like in this operational phase, like the most interesting one, concerning that if we have the funds for the construction, we like already took all the risk and all the negative impact that all the construction of a dam will have to do with it. I think the operational phase is the one that we should focus on. And if we want to, how to say, give the positive approach to the hydropower, we need to like show and compare with the other like solution. I agree completely with you. It has like the completely, how to say, this paradox thing in approaches how to disseminate this approach. But still, there is a lot of inconsistencies, as I mentioned, also in the challenges that there is no like one uniform approach to this method. I think since it is like the new, like it's not the new method that, but has been like recently heavily applied. So all the case studies and all approaches have their own view concerning this. But thank you for this note.
Okay, thank you. And I would like to welcome our second presenter, the Professor George Agidis. He's a professor and head of energy engineering in Lancaster University in the United Kingdom. His career includes industrial and academic experience in the UK and internationally. He has research, design, development, and patent contributions in the fields of fluid machinery and renewable energies, developed turbines for hydropower generation projects, and has physical research prototypes of fluid machinery operating successfully worldwide. His generic research involves the theory and systematic design of innovative wave energy converters, and is also involved in type energy research and development projects. The floor is yours.
Okay, thank you very much. And the chair asked me to cover on this session the next steps on marine energy. So I'm doing all this work in Lancaster, which is, as you can see, in the UK, in the north part, not far away from the Lake District. And you can see it's just a campus university. Just a university, not in the city. And I operate from these three buildings, where we have labs on all three buildings, CB1, EB2, and FST. This is the university, and because I'm involved with energy in general, and I don't have a big river next to me, otherwise I would have had, well, I have a hydropower station done perhaps 20 minutes away from the campus, but on campus is the only university in the UK. We have a 2.5 megawatt wind turbine. No other university in the UK has is covering the needs, 1/3 of the needs of campus by this single turbine. Although just a few miles down, we have 2 nuclear power stations with dedicated connection since the university was built. And just a couple months ago, because I have a lot of Saudi PhD students, I developed on campus again, the only one in the UK, a solar farm that is 14.5 megawatts. So not only will be covering the needs of campus, but it will be exporting to the national grid as well. So coming to the topic that the chair has asked me to cover, we can always integrate hydropower with wind and solar. We have been doing that in the United States for a number of years now, try to support weak grids with wind turbines associated with hydropower, and that's done very successfully. We have very good projects in the United States, and obviously we are looking into integrating solar on dams. Perhaps we could put it in Nevada, for instance, or any European dam, or also have some floating solar that could be done on the above the weir, or in lakes, or in the UK. Some utilities are using it on the waste treatment area where we could have solar farms. And again, I'm talking about the UK here. Come on. In other parts of Europe, there is much more sun included here where we are today. We carry out quite a lot of work on marine energy and ocean energy and wave tides, and we have significant facilities with for unique in the UK, by the way, on for wave energy devices like the Talos. That is quite unique. It's Prozagidi's idea, comes from Lancaster University, and now I'm working with all over the world, US Department of Energy and China and Europe on top of the UK. And also we are doing a lot of work on hydrokinetics because you can see our wave tank has thrusters that I can actually generate tides for tidal energy, or I can generate both tides and waves at the same time for specific applications. And being Greek, obviously you can see the name Talos on my device, although it's specifically for funding from the EPSRC in the UK from London, and it relates to technologically advanced learning energy system, where we're looking into machine learning and artificial intelligence. We have been involved for many years now on ideas for wave energy that require a very specific hydropower power takeoffs. Examples include the aquamarine oyster that you can see here as front, developed by a PhD student, Matt Foley, at Lancaster University. And right at the top, you can see it actually being tested at the Orkney Islands in Scotland at the European Marine Energy Centre. The idea is that you have an oscillator that is moving with the waves. You have a piston, and you pump seawater into a high-head Pelton wheel that is on land, and then it's a normal Pelton hydropower station. Other ideas that are even more unique is this Aquaboy Finavera. This is an idea that started in Sweden, but is being developed at the moment in Florida. And they came to ask me for support to design for them a very high head, very fast, and very small diameter Pelton turbine, specifically for the applications and requirements of their device. It didn't exist before, it exists now. Idea developed for marine applications could be used for onshore applications as well. This is just marinized version. Another idea where we are talking about the opposite, local applications. In Denmark, in Copenhagen, my friend Hans Christian Sorensen has been developing for a number of years the Wave Dragon machine. This includes 9 ultra low head Kaplan machines. And I took that picture one winter day when I became very wet on a dinghy, like the SAS going to visit a Wave Dragon in the North Danish Sea. It was quite a good experience. So we were able to marinize a low head Kaplan machine. And up to that minute, we were talking in Europe globally up to 5 meters head on Kaplan machines. Since then, we developed these machines that, because of this application, have a requirement to operate between 2 meters high and 0.2 meters low head, so this device can operate. Again, we developed this for offshore applications. Why not to put it in a stream that is close to your house, village, or town? No, now we have developed this technology. And you can see exactly how we managed to expand the performance envelope of machines. It was quite a big project that we have been working on for a number of years against what it was disclosed on the EU website at the time. And as I said, I don't have a river next to on campus at Lancaster University, so you've seen wind and solar, but just 20 minutes away, I had the river Bila that I had a weir of 4 meters head and developed. The first day I went to this it is a corn mill, an old corn mill, and I took that picture. We developed a specific Kaplan turbine, low head. It was 120 kilowatts. And this is the plant you can see up at the top. And this is the corn mill with the plant together. The day I connected it and it was producing, and I was leaving, and I took a similar picture to the one I took before, done environmentally in a very environmentally friendly way. We had to develop new modeling techniques to actually do this work, because I had money and I had 18 researchers, professors from all disciplines, and including economists and resource engineers, environmentalists, public acceptability people. The first day when I started the project, it was a very difficult meeting because I had to control all these big egos. Nobody wanted to listen to people that they were not talking about their own discipline. And then they realized that if we want to have a little project or a big project, we can have to work together. And really, a project will take place as long as the weakest link around this process is satisfied. So everything has to work in parallel. If you don't do that, nothing will happen. For instance, we had a stumbling block for this little project because the national power wanted £1 million to connect it to the grid.
it was a showstopper. Just across the bridge, there is a paper mill. I went to speak to them. They were happy to take with a cable the electricity, they're energy hungry, and also they got bonus points from the government because they were using renewable electricity. Problem solved. Moved on. Same with fish ladders and everything else that we were encountering along the way till it's completed. So we had to go through this circle you see there several times, and every time we're going deeper and deeper and deeper till we reach the stage of execution and coming to the correct conclusion. We started also based on flow duration curves. We started wrongly, the developer, with an Archimedes screw, and then when we looked into the potential with the Kaplan, producing annually a much better annual generated power, which translates for them into better annual generated revenue. We finalized the project in this Kaplan. Another area we are working, I'll just give you some examples because there are too many. Another area we're working on is Archimedes screw. The whole world knows about Archimedes screw pumping. Over the last 20 years, we're using it for generation. We have used it in a TMEC for tidal stream applications, never on tidal rains. And this is in my labs at Lancaster University, probably the only research is taking place globally. I have not heard of anybody else doing it. So when big manufacturers like Andritz had to deal with a project in Indonesia like that, they have to come to talk to me so they don't have to reinvent the wheel and progress, from that point onwards with the project requirements. Another one, it's symphonic hydro. I have been doing some tests. You can see the picture at the bottom far right on the river Kent. And somehow one of my students put it online that being picked up by Holland, that they have a problem with their estuaries there. And they came and presented to me my research as a solution to the Dutch problem that with the estuaries they developed back in the 60s, that today it has killed all the fish, killed all the plants. It's an environmental disaster and kills the tourism because of its stagnant water smells. So they want to replace the environmental embarrassment from the past with an environmental friendly solution of the future that will not kill the fish doing it, and at the same time will not damage existing infrastructure and roads they developed on top of the dams. So the idea is, as Holland is tidal, when the tide is up, we can bring fresh water in the estuary. When the water is down, we bring dirty water out into the sea. In parallel, what I have done at Lancaster University, as you can see here, I introduce a pipe into the downward leg where I can enter water. So I have aerated water going down. Aeration is oxygenation and speeds up the regeneration process. Okay? So really, this is an added bonus for them. But the draft of air is passing through. I put a turbine at the top and a generator, an air turbine. And this produces electricity. So as a byproduct of the whole thing, they can generate some electricity as well. So this is a really environmentally solution that for the future, and at the same time, it's friendly, fish friendly.
fish can pass through these massive pipes either way without any problem. Along similar lines, we looked with utilities in the UK. On the left-hand side is Yorkshire Water, where they were interested to use it for generation. And we have carried out successful results outside of Leeds. And on the right-hand side, it's with United Utilities, where they were interested to use the bubbles and aeration on waste treatment plants. So again, this has been a successful solution with a lot of benefits. Again, we are doing quite a lot of work on all sorts of different aspects. Obviously, we looked into modernization and looking at energy potential. I'm involved with Brazil and Brazilian engineers on a number of aspects at the moment, and also with Chinese on other aspects of hydropower plants. We've heard this morning about tidal range and Lawrence. This is an area that we are heavily involved with, and we have a lot of outputs on the public domain. We've been involved on every single project that is taking place globally. And even we mentioned about Lawrence this morning. You can see the picture there of Siwa in South Korea, the largest plant on the world today, and the newest, connected to the national grid. And definitely, like I say, university myself, and you can see my students there. We had a direct involvement on this project, and the man in charge of the project, Markus Schneeberger. Do we have anybody from Austria here? Yes, he's the Austrian Global Vice President for Engineering and Research, Markus. And before going back to his wife in Austria, he was stopping at Lancaster to actually discuss with me, and at the same time, my students having the opportunity to speak to a top engineer globally. This was an awesome experience for them. And because of that work, I had 3 months involvement with the board of hundreds in Vienna. So I had to come to Vienna so many times to allow me to publish the performance curve for the turbine. So this is the only one that exists on the public domain, by the way, now. After the Baker book from the 60s, that they have an old turbine. So this model, you can find it available online. It took me 3 months of communication with hundreds in Vienna to actually allow me to publish it. And you can see the Siwa project. There are about 10 units of 26 megawatts each. The size is quite significant, as you can see there. We're talking about 5.8 meters head, and we're talking about 7.5 meters diameter runner. And you can see the plant in construction phase, and this is the final version. It's so large that if you go on Google Maps and you Google Seoul, You will be able to see it there, just 30 kilometers below Serbia, this project. And another project, talking about tidal rains, is Swansea Bay Lagoon in Wales. This project started in my office from a blank sheet of paper. And because I'm not in Wales, I'm in England, my colleagues and good friends from Swansea and Wales were complaining why I'm doing the initial model, not them. But regardless of that, this work has been done. And in parallel, I have been working very closely with Andritz engineering in Austria and also Ravensburg in Germany. And here you can see the global vice president for hydropower, Ben Hindenburg, of Andritz in he's based at Ravensburg. And he's at Lancaster University, where we have a very specialized rapid prototyping machines. Probably there might be about 5 of these machines in the whole of the UK. And we printed this in multicolor printer, the Andritz turbine that we developed with triple regulation. And again, this is dates back to 2017, and this is the first time that I collaborated with GE on the electrical part and Andritz on the hydraulic mechanical part, and we came up with the first time on the world, I think, for a Tidal project on a device that is triple regulated at 20 megawatt size, a single device. And okay, as I said right from the beginning, I'm an engineer, but I try not to have a big ego about engineering. I try to work with anybody that could help from other disciplines, exactly what we try to do. So I had a number of research students from the School of Architecture of Liverpool University. And we looked, this is Liverpool, by the way, and we looked into a project that, do I need to press a button, anybody, guys? This thing, okay. And we came up with a project, it's available on the public domain, by the way, where we looked into anything beyond energy generation. So we looked into developing international landmarks. So you can see a click of beyond of Singapore, for instance, linking communities between the two sides of Liverpool and integrating wildlife, creating a global hydropower research facility there, and so on. We called it the Green Whale. And really, we looked into other aspects beyond energy and environmental, societal, and economic opportunities. It was so well taken at Liverpool that the Radio City, the main radio station of Liverpool, was discussing it with men and women of Liverpool for a full day with positive comments, the output of this work. Also, I spent quite a lot of time with British politicians. Every week, I'll have at least few emails with politicians from the House of Parliament, because anything to progress in the UK in a positive way has to be predominantly financially done in the UK. So we started with an Andritz turbine that is made in Germany, but really we try to, with the help of Andritz and GE as well, we try to see how and who will actually manufacture it specifically in the UK. And we try to maximize the British flags, as you can see, and minimize the non-British flags. So the politicians, whoever they are in London could actually agree to just progress with projects like Tidal projects because we have the biggest resource in the whole of Europe, and the 50% of the resource is on the west coast, exactly on the projects that are around the coast where Lancaster is based. And at the same time, on the background, not advertised because of confidentiality reasons, we're looking to all different technologies. So at the moment, we're looking to large coupled turbines, unidirectional or bidirectional as well. We're talking about turbines that are operating in the mid-90s. We're looking at the other end, batch limited open stream turbines. And as we speak, I'm working with this Rolls-Royce idea in the middle, where for climate change, we're looking to new technologies that we can be fish friendly and with similar efficiency, very close to the left for both turbine and pumping. And this is probably new technology that doesn't exist today. And thank you very much. I got your message. Thank you.
Thank you, George, for your beautiful presentation. I know we have time limitations. And I know that our roundtable discussion suddenly is becoming a presentation session. So, George, please stay. I think we will continue with a few questions because we have another presenter afterwards. Do you have any questions to George on your presentation? Yeah.
I have one. Thank you. Can you explain more in detail how that device works that uses high pressure Pelton for some ocean application? I didn't understand how it flows and so on.
Yes. This one.
No.
Yes, this one.
This one.
No, okay, this one, not this one, but the next one.
The next one.
This is Pelton version.
Yeah. Not this one.
Not this one.
This one.
Yes.
Okay. This one has
George, you can take my. Thank you, Sean. Yeah.
as the waves are passing through. Yeah. This buoy is moving up and down. It has a massive weight at this location. The massive weight, because of inertia, tries to stay still. So you have something steady and something moving up and down. You have a rubber material that pressurizes water, and the pressurized water, it's sent to a Pelton wheel, very high head Pelton wheel, very fast running, and then the spent seawater flows back into the sea. Are you happy with that?
Okay, thank you.
Okay, and Sebastian, the other one, since you asked for it.
Yes.
Again, for an environmentally friendly solution, we use seawater. So the waves keep this flap moving. This flap moving, it has a piston here. The piston pressurizes seawater, and this is a normal hydropower plant. And then seawater back into the sea. Is that clear? Yeah. Thank you very much.
Yeah. So, is there anyone like us have a question? If not, perhaps, yeah, Sebastian. Then I would like to also,
Yeah.
because I think we are running out of time to have roundtable discussion. I will ask the question that I was prepared for the roundtable. 10 years ago,
Sebastian?
yes, I will give Sebastian also afterwards.
Yeah, okay.
For me, it's a tricky question from my side but I don't will I will not find another person to ask this question.
Okay.
Young Lithuanian guy 10 years ago defended thesis about sea wave energy in Baltic Sea, and I remember it was the same beautiful summer day, so 10 years ago, and during this time I am keeping all the time at the wave energy development. My ear stays in my heart because it was the first PhD defense in Lithuania on wave energy. And I'm thinking now, 10 years passed. 10 years ago, it was developed, I was talking this developing technology.
Yeah.
10 years passed, it's still developing technology. So I just want to ask you, is wave energy really in trouble with how long should we
Not
still
at
wait for the
Not at all. With any,
technology to develop?
I understand. Thank you. With any new technology, you need to pass from a period where you have many ideas, and then start consolidating the ideas till you find the one that it will be the most widely acceptable. And we've seen that with anything. For instance, on wind turbines, that they have perhaps 30 years head start to wave energy. We started with a single blade, 2 blades, 3 blades, vertical axis, horizontal axis, harmonious, and all sorts of different ideas. Till today, we don't have 100% yet, but 90%, I would say, we would be on a horizontal axis 3-blade machine consolidation of technologies. If we have to follow that route, we need the 30 years development on wave energy to actually consolidate new ideas, because there are so many ideas. You can find them either at the EMEC website that I was instrumental to develop. Together, I helped also US Department of Energy to develop their own similar website. And you will see there that there are many. But now I'm just really pushing forward with new ideas. For instance, the one that I moved on, it was a multi-axis and omnidirectional, the Talos idea, that the UK government immediately, when I presented to them, gave me £1 million just to progress with it. It was not Cambridge, Oxford, or Imperial. It came to Lancaster University to develop it, and it's so exciting that the Chinese immediately are doing it as Young University, and the US Department of Energy are meeting with me every week to just work on this idea. So things are progressing in the background towards consolidation. And halfway between the two, we can see tidal stream. That at least on tidal stream, you can see that they begin to slightly consolidate these technologies. Now, on tidal range, it's a different story. It's financial. The problem is that in the UK, the politicians have very short vision, field of vision. They can only see every 4 years, and in 3 years, they start canvassing for the next 4 years, and not on a project that it will be large infrastructure project that will last for 120 years. So they cannot see so far into the future, although we have excellent examples in the European Union. For instance, in Sweden, when they built the North-South Road, A69, whatever it's called, ministries got together, different ministries, from transport to energy and everything else, and they build roads together with energy related. So they have tidal, they have wind, they have solar, they have everything right from day one, like from a blank sheet of paper, they started that. So there are good examples to follow there. Okay?
Thank you.
Thank you.
Yeah, Sebastian, last, especially the last.
First, Georgios, thank you for your presentation. In my view, the presentation with very deep understanding and very wide distribution of the solutions to develop the idea, to testing, that is, in my view, what maybe is part of the education and development in the system of the education, because the student they have the chance in order to thinking, developing, and to implement. Thank you for this nice presentation. And maybe one comment here. You mentioned high turbines. In my understanding, maybe it's better to thinking to be low specific speed machines. The meaning maybe the head is not so high, but the discharge is very low. And for that reason, you are talking about the Pelton machine here, because we don't have the numbers in order to understand how is the specific site configuration to understand what means high head turbines. Because generally that is what we understand for hydraulic motion.
If you want some specific space for the Pelton drains, because we're talking about use, it's fine. Yeah. Yeah, thank you very much for this. Apologies for not clarifying that. It was a very high pressure application, which was the specific speed in the Pelton range. Never mind the flow. The pressure was significantly higher than anything we have seen so far. This is why I mentioned that it didn't exist, because to make it, I had to run it in speeds that are similar to the speeds that I'm familiar now with, let's say, massive Sulze oil and gas pumps running on oil fields. So it doesn't exist. So it's something completely new. But this is just skimming the top of the surface of the projects that my students and me are involved in. Yesterday I mentioned we are developing new ideas, novel ideas between Pelton and Tempo Impulse and many others that inline turbines, all sorts of things that I just try to focus it because of the strict instructions I received from the chair on just that subject and nothing else. I'll be happy to another occasion to talk about beyond that as well. Too many projects. Thank you very much for the question.
Yeah, thank you, George. Thank you. So, perfect. And yeah, welcome. Our next presenter is Sergio Pakalis. He's an assistant professor of energy processes at the School of Chemical Engineering, National Technical University of Athens. He's also scientific advisor for the Hellenic Ministry of Development for the Greco Islands Initiative that promotes sustainable development, green economy, energy autonomy, and digital innovations in Greek islands. Yeah, that's one of the topics. That's why Sergios was invited. So together with his team, he works on the design and modeling of renewable energy sources, and he is still involved in University of again, he is principal investigator in the Horizon project via net. So the floor is yours.
Thank you. Thank you. Do you hear me?
Yes.
Okay. I think you hear me, no?
No.
I can just walk around, you know. Yeah. It's more about making a conversation, less about making a presentation, kind of help transition to the next questions that you have prepared. There's so much thought. So, okay. So, what's the idea? I would like to talk to you about some things that we have done recently in Greece in order to accelerate our green transition, but also at the same time interconnect the more, let's say, conventional renewable energy systems with hydropower. So overall, the mixture in Greece has kind of changed during the last decade. And our main source of fuel was lignite. This has been phasing out rapidly. And natural gas now is the name of the game, but also you see a lot of variable renewable energy systems are entering the grid. Also, an issue that has to be, let's say, communicated is that we need a lot of import of energy from other countries in order to balance the electricity usually. There are some areas that have been suffering the economic damage of the closing lignite plants, and this is something that has been addressed by installing a lot of photovoltaic plants in these areas. And this, in some cases, has created some issues that I would like to discuss today. Hydropower is one of the big three in Greece. It has been historically one of the big three. We have approximately 3.2 gigawatts of hydropower. But in order to be consistent on a yearly basis, we kind of get a 10% capacity factor of operation of these systems. You see that the main areas that we have the operation of these hydropower plants is usually in this central area of Greece and also Thrace. It's about our system with the four rivers. I'll just go fast. I don't want to bore you with the numbers. It's our four river system. Aliakin is shown twice. Also, this publication was referring to the river Aos, mistakenly skipped primarily the river Achelos in Greece, that has the bigger hydropower potential in Greece, and also has the bigger power plants in respect of hydropower. I will move very fast. This is our main, let's say, bigger plants, Kermasta, Polyphyton, Thesauros, and Lian, what's the name? Liarenas. The thing is that in respect of this, you see that this upper part of the table, we have this Achelos, let's say, group, which has a lot of potential for this. We do have the existing infrastructure to produce a lot of power from hydro, and the conversation is how do we actually manage the two systems, like the hydropower and this rapidly evolving VRE systems that are very much transitioning from one hour to the other in respect of power production. So we have a new energy plan. It came out a few months ago. That is a little bit, let's say, it has raised more questions that have solved previous problems, and we have discussed it a lot with the other needs in this community this day and the last one. And as you see here, what is being planned for Greece is almost the 8 times multiplication of the photovoltaic systems, and also 3 or 4 times the advancement of wind power if you also include the offshore technologies. This is problematic in respect of how are we going to manage the penetrations of these VRE systems, and how actually are we going to answer the questions of stability, grid stability. And in this situation, actually, I think that this is the perfect place to discuss about it, because hydropower will be a significant part of the solution, at least for Greece. So this rapidly, let's say, developing VRE technologies that are being installed have a lot of issues in respect of their stable operation, as you already know really well. The thing is that they are distributed around most areas, but we have this higher, let's say, concentration of photovoltaics in the area of Western Macedonia. This is the places where we have the older coal plants that now have been shutting down rapidly, and we have the new photovoltaic plants being developed there in a very rapid scale. The issue is that at the moment, we have so much production of electricity that we are curtailing, we are cutting let's say, the amount of energy that the producers are able to put in the grid, in sometimes percentages that are above 40% of the production, which is madness. And at some point, they need to go compensated. And as we were discussing yesterday, it will be the grid taxpayers who will pay the money. It's always the case. So the thing is that sometimes when we manage to work both wind and solar, okay, we can a little bit, let's say, normalize the fluctuation on a seasonal basis. But in any case, we're not able to normalize the production on an hourly basis. This is always an issue with these situations. And in any case that we have the wind power goes down, we always have the ramp up of the gas engines. Low efficiency gas production from gas turbines and gas engines that is not only problematic in respect of the energy production, but also of the CO2 emissions. And this is just a small graph about the price of electricity that is being produced from different systems. And as you see, the ramp up engines. Here, gas peaking, you see, is by far the most expensive and creates a lot of issues in our country about the price of electricity that we pay at home, to be honest. So one solution that has been discussed extensively, and this is part of my work that I'm not solving today, is the concept of power to X. Using this excess electricity to do something in the media like hydrogen, and then we do something with the hydrogen. Usually what we do with ammonia, we convert it to biomethane and stuff like this. There is a lot of issues and a lot of conversation that has been put in this idea. So a few years ago, Denmark and then a lot of other countries followed and said, okay, yeah, power to X, perfect. Not perfect. First and foremost, electrolysis needs a lot of electricity for every kilo of hydrogen that's being produced. We're talking about 45 to 50 kilowatt hours per produced hydrogen. On a secondary level, we are seeing that this green transition that was put forward within Power EU has been kind of been in a stop right now, due to the case that right now we have seen that a lot of these fluorinated membranes that are used for the electrolysis and the fuel cells produce a lot of PFAS. If you remember, if you have, let's say, been in a discussion about PFAS, we're talking about substances that are called forever chemicals. They are very toxic and carcinogenic, and they are actually everywhere when we are discussing the production or the utilization of green hydrogen. So it's a conversation that has to be done. So also an important situation. We're not only producing electricity, we're also managing the frequency of the grid. Spain was an issue a few weeks ago. So we see in Greece that when we need to manage the frequency, to ramp up the frequency, to support the national grid, most of the time it's hydro that is doing the job. So in respect of having this in mind, that I will show you also one other sort figure in a little bit. The idea is that we will have approximately 4.3 gigawatts of batteries that are going to be installed in order to support this excess electricity from the VRE systems. But as we all know, the batteries that are going to be used, they don't really have a very long time of operation. We're talking about contract based, they're obligated to work for 2 hours. So this is kind of problematic. On the second level, we have this capacity, which is 5.5, and I mistakenly, when we were talking yesterday, the Greeks, I said 6.5, and you were right, 6.5 is a big, it's 5.5 gigawatts of power that is going to be installed until 2050 increase in respect of pump hydro. We have a national strategic plan of developing the Amphilogea pump storage system that is going to be finalized in 2027. It's being funded by the RSF. It's European money, so it will be done because we found the money. It is a lot of conversation that has been done around the situation. The big issue and the big importance of hydropower is when you see the daily demand. Sorry for the great business, was a little bit last minute, but I wanted to show you that as you go through the day, okay, we have this afternoon peak, as we have discussed between us yesterday in the tables. It's always hydro that is there to fix the frequency and support with high value electricity in the grid when we have the rapid decline of power production for photovoltaics. And keep in mind, how the situation is going in Greece will develop in a crazy nightmare like California. You see all this photovoltaic production, electricity production during the day that you can do nothing with. Okay, so we have to store something, we have to pump something. The thing is that if we are talking about multiplying 8 times the production of electricity from photovoltaics, you can understand that when we already are curtailing, in some cases, 40% of the produced electricity, this would be a much bigger problem. Okay, so except from this Amphilogea project that I told you before, we also have the project in Amari that you will see, but also projects in the mainland. So Veria, Peloponnese, that will be in the next few years, will be up to 1.5 gigawatts of power. So the energy mix I showed you before is really about the mainland grids. And this was something we discussed, the two of us, extensively in a previous conversation, that, okay, we have the mainland grid, but we also have a lot of islands, but they are isolated, they are not interconnected, and they get their electricity from diesel engines. Diesel engines, 2025. So the thing is that except from the very low quality, environmentally speaking, they produce expensive kilowatt hours, up to 400% more than the electricity that's being produced in the mainland. So this is something to be discussed. There have been decent efforts to integrate renewable energy systems in the grid, but most of them have been, for the most part, VREs, solar, wind. You see here actually the best cases of renewable energy penetration in the grid in the bigger islands of this, where you have some fluctuation. Okay, and you see that usually it never really exceeds 15%. We have some cases of renewable energies penetrating the system more than 20%. We had also the case of Lesbos recently that made a resurgence, but this is it. So we're talking about green transition and everything else, but this needs to be done in support with a support mechanism. And we discussed in Greece and also European Union had the same idea to have some islands being the blueprint of a green transition. If you can do it on an island, we can do it in a country. Sounds great, not a good idea when you apply for it. So we picked a few islands where we tried different things. And we have some interesting solutions. And actually, it's totally by chance that our area of the North Aegean, where Lesbos is and the other small islands I will show you, we're doing the best. I'm being objective here. I'm being objective. Okay. So we also have this European project that we did with a lot of partners. It's called React, but we also try to do a similar process. So we had the opportunity to collaborate with international partners as well, see what they're doing, and try to emulate. The basic idea, and what you have seen again and again and again in green islands, is PV, wind, pattern. Okay, this was a similar approach. It had the additional part of controlling the demand and response of the grid, which is a good idea, but we don't have yet the smart devices to account for this type of fluctuation. We tried also immobility. Great idea for a full application. The whole island of Astypalea needs 1 megawatt of power during the winter. If we connect 8 cars in a Type 2 charger, 1 more megawatt. And the plan is to have 420 cars on the island. Okay, great. What that's actually kind of going to work is our Ios Stratios, the small island in the North Aegean that will be permanently non-connected. So we try to figure out a solution for it to be green in the long term. And the idea is to combine photovoltaics, batteries, wind, and also district heating to account for the excess electricity. Again, a similar idea. What we actually figured out with this is that in the island cases, wind power is being the dominant force. So we were talking about the mainland before, we're talking about the photovoltaics and how we're managing this excess production, especially in the area of West Macedonia. But now we see that in the islands, wind becomes the dominant force. So how are we going to manage the excess electricity from wind? We see in the case of Ios Stratios that actually three times, we produce 3 times the electricity that is necessary. So we have 65% excess electricity from the production of 1 wind turbine for the island. So we need to do something with this. Okay, and just to let you know, in the whole year, if you have a conventional system, system that works normally, if it has 1 megawatt, it produces in the whole year, let's say approximately 8,000 megawatt hours, let's say the whole hours of the year minus the downtimes. Okay, variable renewable energy systems have the capacity factor. You usually get a third. If you are likely 40% of the nominal. So this is one thing. When we're talking about, okay, we're missing a gigawatt of power. You're not missing a gigawatt, you're missing at least 3 if you want to install the nominal capacity. Also, the issue of the wind power. Every different wind speed correlates to different produced power. We have the power curves of it's different. Turbine, this is just one typical one. Not all of them work the same. But you see, in order to get this nominal 1 megawatt for this wind turbine, you need to go up to approximately 11, 12 meters per second of wind speed. So we get fluctuations. What also fluctuates is the actual wind speed. This is a typical variable distribution. So in different times of day, we have different wind speeds. And this we have to account. So let's go to the actual things that we have done on the islands. This is the case of Ikaria, and we have with 2 wind turbines of 2.7 megawatts. But everything they do is they pump the water up to a pump hydro system. They do not give electricity to the grid. They just pump it. With this idea, they have increased the renewable energy penetration in the grid more than 50%, which maybe sounds to some of you very average. It's actually very big in respect of a small island. This is the great emblematic project that we're trying to develop in Crete. Amari is a very historic village in Rethymnon, where the idea is to try to valorize the existing huge wind potential of the eastern part of Crete, especially the wind power of Lasithi. And as we were talking yesterday, this wider area has a very high wind power potential in respect of the whole country. So the idea is that we will have 3 turbines, 2 of them are guaranteed to work all the time, like the 50 megawatts, and then the other one will work occasionally. So this is something that will change the whole, let's say, stability of the network, taking into consideration that Crete now is interconnected with the mainland Greece. But another thing that needs to be communicated is that except from the actual, pump hydro, wind power production, is also the fact that the Greek national grid electricity is very old. We are losing more electricity to transfer the electricity from the one part of Crete to the other than we are losing to move the electricity from Crete to Athens. Because we have the new high voltage cable. And now let's go to Lesbos Island, which I'm trying to convince you to make a meeting. So the idea is we have the new Eresos dam that is connected with the new pump hydro system that is going to be developed very, very, very soon. The idea is that we have the idea of installing 18 more megawatts of wind power. At the moment, we have only 11. And again, this wind turbine will be interconnected with a pump hydro station that is approximately 15 megawatts of power. And this system has actually the interesting point that it's not going to be only a power unit, but also a unit that will also be used for sustainable irrigation. So they are helping both activities. And this is something that, if you have patience, you can actually look our idea about the Carrion Ferry hydro dam in the United States. So this is something that it would be very interesting for us to look into the next few months. If somebody has the time and the energy, more than happy to work together, to model it, to analyze it, and maybe publish something. So I will just close the presentation with a couple of nice images from Eresos, where it's a new dam. So it's one of the longest bridges that you can find in the Greek island. And also, Lesbos is the motherland of Ouzo. Okay, it's the Ouzo Museum and also the very famous Ouzo you see here.
It's still the silent.
Yes. So you're all welcome to join me in Lesbos whenever you want. Thank you for your attention.
Thank you, Steph. Don't run away. I think we still have time for a couple of questions. So we need some hands. Yeah. Here, Larry.
Thank you very much for this. Thank you very much for this analysis and of Greece. I was just wondering because there's a huge interconnector being built.
Yes.
There's a huge interconnect. There's a huge interconnector being built between North Africa and the Crete, right? It's a 2 gigawatt, if I can I mean for actually. And Greece is also kind of a turning point for energy because you're selling over to Italy, to Albania, Serbia, where the prices are, I just checked it right now, the stock prices are sometimes multiple times higher.
Yes.
Yeah? So I was just wondering how this fits all into your analysis that in the future you will be even more a turning point of energy, receiving energy from North Africa and distributing it to the other Balkan countries.
I think I have now it works. It works. Okay. Okay, sure. Yes.
Yeah.
Okay. Okay. Thank you for the question. It's excellent. Actually, to be honest, for the most time, we are fine with these people being in Serbia. Yeah, because they have the hydro that they produce, especially in Albania. This one, it's okay. No worry, no, it's okay. It's okay. Uh, wait, so I guess just to repeat the microphone, we are the ones who are most of the time buying. The high prices are actually due to these fluctuations of these renewable energy systems that we're not able to manage properly at the moment. We have issues with how we are stabilizing the grid. The, the storage systems, especially the batteries, have taken much longer to develop than expected. We are expecting by the end of the year supposedly 900 megawatts of storage. Now we have 200. But the problem with batteries is that they only have 2 hours of operation by contract, and we only have one of the systems that will be able to work up to 4 hours. And you know, I think the aspect of price is a little bit problematic in our case. In respect of the trade with Italy, we're mostly exchanging natural gas. So this is a two-way system, and for us, we were expecting that we would move to liquefied natural gas. We also invested into new FSRU units. But what really happened is that we are back to using the conventional pipelines. So this is an ongoing conversation about how we're going to manage the natural gas and the declaration with Italy in respect of this case. Now, the Egypt situation is developing. We'll have to see. And it is an excellent point that you make. But I think we have only discussed about it. I don't know anything more than you do in this case. We have more.
Very interesting presentation. Thanks. My question goes in direction for the small islands. Are you trying maybe to use also the salt water as a power storage in the power storage system? We made some analysis on this way for different islands. It would be nice to see how this can be done. Of course, it's a lot of other challenges what we have, but possible to solve. Thanks.
Okay. No, I can say it. Wait, no problem. This is an excellent point, especially for the very small islands that do not have valuable land. I agree with you. Look, there is the island of Kalki, which I didn't mention today. Wrong from my side. I apologize. They are very much advanced. It was the first island in Europe that became 100% renewable, but they are interconnected with Rhodos, which is a much bigger island. So Rhodos being kind of the battery of them. So they're giving everything that is in excess in the morning and they take back with the net metering system. They are looking into exactly what you say. And this would be a very interesting case for us because it is a case for stabilizing the grid and also not having the problem of, we have issues with water, which we don't have a lot actually in most of islands. So this would be an excellent case study, and if it works, yes. But in these bigger islands like Lesbos, for example, what we are trying to do is find a common ground with the ecologists and try to also use it for things that are, like irrigation and also, the whole water management system of the island is a main issue of discussion and conflict at the moment in this situation. And this is, of course, something that I would like to see. I will keep it very close, and there will be a good opportunity to get back to you with more information. So next year in Thessaloniki.
We have one more question.
Oh, yeah, so this works.
This one, okay.
Just to respond to this question, I think the solution which is investigated at the moment is to use desalination and use a clean water in the pumped storage process rather than directly use a salty water from the sea. Because technologically it's quite much more challenging and expensive combination. For this is the intermediate solution.
Yeah, what the professor said is absolutely right. There is a lot of modeling. Yes, that works. Of course. Perfect. Okay. Now, what the professor said is 100% spot on. There is several studies, modeling studies for big big universities and upcoming researchers that are incorporating salination as a system of managing the excess electricity. Of course, this is exactly what's happening right now. I didn't went that far. My daughter just wanted to to reply directly to you, but I agree. I agree. Of course, this is one of the ways.
Yeah. Okay. Any final remarks? Any final questions? One question. Okay.
I have a question. If you have experience with a system like photovoltaic hybrid system with photovoltaic wave converters and batteries, do you have some instances in Greece that
Yes.
yes?
Actually, then I don't know if you have okay. Yeah, sorry. No, actually, the case of Iris Stratios that you saw in Ireland, is being developed by one of my ex-PhD students, former PhD students. So we have a very close collaboration with this. Also, the new big several gigawatts photovoltaic farms that are being developed in West Macedonia are also being developed by previous students of mine. So we know very well what's happening in respect of the production. There is this spike in the middle of the day that we're not able to manage. And what is being communicated to us, and Professor will also maybe has more information about we have one big remaining lignite power plant in Ptolemaida 5, which is one of the state of the art. Let's say lignite power plants in the world, and this is not an exaggeration. They were communicating to us that, of course, they have to account for this overproduction during the day, and they try to usually they use an extraction valve, so they try to put away this part of the steam, not to throw the turbines. But in this way, they are reducing the efficiency a lot. The isotropic efficiency of the turbine gets lower, and also the emissions of the operation of the plant becomes higher per produced unit of energy. So the interconnectivity between the two is at the moment a little bit problematic. Did I answer your question? I think the battery part is not yet in full operation in the area of West Macedonia, and we know in advance that we don't really have a lot of hours that we're able to pay with it.
Installation in the Beast Island in the Adriatic Sea, Croatian part of Adriatic Sea. For that reason, I ask you. Okay.
We should talk for sure. It would be very interesting to exchange stories of less success than expected. Okay, do we have one more hand or not? Okay, so I need to wrap up now. Yeah, huge applause for our presenters.